Welcome to this video on dynamic discrete choice and dynamic demand. What I'm going to do today is to talk about the paper by Hendel and Nevo that came out in Econometrica in 2006. And the big topic here is that static demand models do not account for many things. For instance, past prices and inventories, and the consequences of that is that we might make a mistake when we use them to predict long-run own price and cross-price responses, and this could lead to severe consequences. So for instance, we could misjudge whether a merger is desirable or not, because in order to evaluate a proposed merger, we need to know about cross-price and own price effects. What are the building blocks of the model? To jump right into it. In each period, in their paper, households decide how much laundry detergent to buy, which brands to buy, and how much of that laundry detergent to use. Now you can say, well, laundry detergent is a very funny product. And that's true, but laundry detergent is actually a great product to study here because it's storable and it lasts forever, right? And in marketing, what people often do is they try to find such products. So the opposite would be yogurt, because yogurt is a perishable product, so it goes bad, so you can't store it forever. So here, laundry detergent, and the way Hendel and Nevo think about buying laundry detergent is that brand choice is important mainly at the moment of purchase. And here, prices and advertising are important, but once people have bought laundry detergent, all they care about is whether they have enough at home to do their washing. Okay, households can store the product at a cost, so there's an inventory, and they can use it in the future. And of course, there's a consumption decision as well. So there could be the following response, that when laundry detergent becomes much more expensive, people might actually use less of it. Households in this world face uncertain future prices and uncertain advertising, so they have to look into the future and form expectations about these quantities. And the whole model is estimated using weekly scanner data. What you should keep in mind here is that inventory is unobserved. But technically what the authors do is they assume the distribution of initial inventory to be known, which is actually more relied on when developing the model and developing the estimation strategy, but is not really a crucial thing you should worry about too much at this point. What I'm going to do is to talk about this a little bit more in terms of data and descriptive evidence. I'm just going to show you a bit of background information. Then most of the time I'm going to talk about the model and technical details that are relevant, of course, in their specific context, but what you will see throughout is that there will be much more general takeaways. And in the end, we're going to talk a little bit about results. What they use are weekly scanner data from IRI. This is a fairly standard data source in the US context. They use information at the household level for purchases and at the store level for prices and advertising characteristics. And first I'm going to show you table 1. It contains summary statistics at the household and purchase level. And what you should keep in mind when you look at table 1 is that this is for the US. There they use ounces as a unit of measurement, and 64 ounces correspond to 1.9 liters. And as far as I understand, these are fluid ounces. So that's a measure of volume. So here we go. So you see in the columns mean, median, standard deviation, min and max, and you see three parts of this table. So you see demographics, purchases, and store visits. Okay, and the table note tells you more about this. So demographics, this is really one observation per household. Purchases, this is one observation per purchase, and store visits, it's one observation per store visit. Yeah, you see like what is relevant in terms of the context. You can think of price responses and storage costs, etc., as being income dependent. You can think of differences across household size, differences across where they live, so suburb or not is the information here, and they actually estimate the model also by group. Then for the purchase data, you see price. So the mean price in dollars is 4.38. The mean size is a little bit more than these 2 liters, so 80.8 ounces. Mean quantity is 1, conditional on purchase. The duration is the duration between purchases, so 1.5 months, roughly. People do switch brands, so the number of brands bought over 2 years on average is 4.1, and the brand Herfindahl index tells you also something about the concentration across brands. For the store visits, people also visit different stores, so 2.38 on average, and here you see also that you can express this in terms of a Herfindahl index. So table 2 is about purchases, or actually about market shares of the products, and what you will see here is that they're actually either liquid or powder detergents, and that within each segment, the top 11 brands actually account for 90% of the market. So it's a very concentrated market actually. And that's the top 11 brands. That's not 11 different firms, as we will see. For these summary statistics, what Hendel and Nevo do is they define a sale as a price that is at least 5% below the modal price of each UPC, Universal Product Code, and such a sale goes along with a 12% discount in price on average. Then, as you might know, there are 2 types of promotional activity that are recorded in such data. One is feature, so that is that the product is mentioned or showcased in, for instance, a retailer bulletin, and display. That means that the product is displayed differently than usual in the store. So here we go for table 2. As you see here, we have the liquid detergents, we have the powder detergents. Here we have the brands respectively, and this is what I mentioned before. Here we have the firm, right? So when you look at the top 11 brands, then you see here the cumulative share. So that means the top 11 brands account for 92% of the market. But when you look at this here, then you see that these are less than 11 firms. So that means that the market is actually even more concentrated than what you first thought. Here you see the market shares. Okay. So the biggest brand is Tide by Procter & Gamble with a share of 21.4%, and 32.5% of the quantity is sold on sale, which it also states down here. Similarly for powder detergent. Table 3. That's actually an interesting table. This talks about, this shows something about quantity, discounts, and sales. So again, you have separately liquid detergents and powder detergents. Here you have the different sizes. And let's just focus on liquid detergents. It's similar for powder. What you see in the very last column is that most of liquid detergent is sold either in a 64 or in a 128 ounce container, so that would be 2 or 4 liters. Okay, here you see how many weeks. This is the fraction of weeks for this to where this is on sale, this size. So 10 to 17%, right? So 11.5 and 16.6% of the time this is on sale. What you see here is that the quantity sold on sale is actually bigger in percentage terms, right? So when this is on sale, then people do buy more. And what you see here is, well, here you see the average sale discount, 15.7%, 18.1%. And here in the first column, you see the quantity discount. What is the quantity discount? So when you think of the price per ounce, how much is it cheaper when you buy a very big container? Controlling for sale. Okay, it's 29% cheaper. So when you look at this, you get an extra discount for a really big container. So that would be like 8 liters. But the real discount you already get, like the most of the discount you already get when you buy 64 ounces instead of 32. Or put differently, if you buy 32, that would be 1 liter, then you already pay 20% extra, roughly. Good. So that's already the background to all this. What I'm not going to do in this presentation is to turn this into knowledge clips or something like this. So I'm just going to have one presentation, one video here. This is a very natural moment for you to hit the pause button just for a sec if you want to have a break. And what I will do next is to talk about the model. So what's the setup? We have time periods T. Think of these as weeks. And in a time period, what a household does is that household uses CT units of laundry detergent, and what this gives the household is a flow utility. And that flow utility is specified in this way here. It's simply CT plus nu that is then translated into a utility. What is this nu? Nu T? Nu T is a shock to marginal utility, and as you can see, when nu T is positive, then that actually means that less consumption leads to the same utility. Okay, so you can think of a positive shock in terms of nu as being a negative shock in terms of consumption needs. And theta is a parameter vector for this flow utility function. Then this is what ultimately drives consumer behavior. They want to use laundry detergent. And now let's think about all the associated costs. So there are J brands of laundry detergent. They're indexed by 1 through capital J. But as you can already see in the first bullet point, the particular brand that they buy does only affect the household's utility at the moment of purchase, but not at the moment of usage. At the moment of usage, only basically the sum of these consumptions, brand-specific consumptions, affects utility, if you like to write it like this. At the moment of purchase, what we do have is a very standard multinomial logit model. But let's look a little bit into the notation here. So what we have here is a choice indicator, and that is indexed DJXT. So J is the brand, X is the size, and T is time. Okay, so that brand choice indicator is 1 if and only if the household buys size XT of brand J in period T. We have multinomial choice. That means that if I'm summing up these DJXT over J and X, I'm going to get 1. X is equal to 0. The outside option is a possibility here, and therefore I'm getting that this is equal to 1. As I said, households derive utility from buying particular brands. So here you have a relatively standard specification for a utility function, indirect utility associated with purchasing a brand J of size X at time T. So it will be alpha times the price plus a brand size fixed effect that will be treated as a parameter and will be estimated, plus beta times AJXT. So that's a vector with the two marketing activities, feature and display, plus epsilon JXT, and that will be our standard type 1 extreme value taste shock. Let me also present you the notation in terms of a table. That is actually stuff that will come in the following slides, but it's useful to have that already in one place before we get there. So we have a discount factor delta. We have the begin of period inventory, IT, and the inventory in the next period, IT plus 1, is the inventory in this period, plus what I buy in this period minus what I consume in this period. Then I have these choice indicators DJXT. They're collected in a vector DT. Then I have a vector of prices. So these are all the prices for all size brand combinations at T. They're collected in the vector PT. Then I have the advertising activities, the two advertising activities for each brand size combination. Then I have all the taste shocks collected in a vector epsilon T, and all the state variables that are relevant for choice at time T are collected in the big vector ST, and that vector contains the inventories, the prices, the advertising activities, the new T, that will be the shock to consumption needs, and the taste shocks for the purchase part of the model. Good. So what does the optimization problem look like that households actually solve? So they choose two things at time T. They choose consumption and they choose what to buy, and that implicitly means they also choose how much to buy. What do they maximize? They maximize flow utility plus continuation value. So let's start with this continuation value. So that continuation value is implicitly defined by the corresponding Bellman equation. That's coming on the next slide. So think of this as capturing effects such as when I buy more today, then my inventory tomorrow will be bigger, and that will be of value to me tomorrow. And that runs via the state transition from ST to ST plus 1, which of course is influenced by CT and DT. Okay, so the two choices households do make. Now, what drives everything that is happening here? Well, of course, flow utility. So this is where we have to take a closer look. So what is flow utility? First of all, here I have the consumption part of the model. So ultimately, what I'm deriving utility from is consuming laundry detergent, and to be specific, consuming a particular amount. So the brand does not matter here. And I have these no T-shocks here. Then I have an inventory cost. So the more I have at home, the more laundry detergent is filling up my basement or some other shelf, the worse for me. And that is modeled in terms of an inventory cost. And that also depends on parameters that we will be estimating. And then the third part of flow utility is this part that has to do with the purchase stage. So what is happening there? I'm paying so for a given X, I'm paying a particular price, and I'm getting a particular utility associated with buying that JX combination in the end of the day. So here I have my choice indicator, and that just picks the corresponding indirect utility, including the taste shock. Okay. So at this moment, it's good to simply it's helpful to think of this for a moment, ignoring the brand choice part of the model. So really, this is a dynamic model where you have a consumption decision and you have a decision how much to buy today. Okay, and what really matters here is which prices I'm facing today. Okay, so when the price today is low, then I will buy, and I will take into account that tomorrow I will benefit from that. So I talked about this continuation value. This, I said, is implicitly defined by the corresponding Bellman equation. So here's the Bellman equation. The value of being in state ST is given by the max over the choices I can make at time t. And what I'm maximizing is what I just put up as the formula in the previous slide. So it's flow utility plus delta times the expectation of the continuation value, and what I'm taking the expectation over is ST plus 1 given ST, given CT, and given DT. And what you see here, of course, is that I'm having here V, and I'm having here V. Okay, and that should look familiar. Good. So when you think about this, then you realize rather quickly that this is a fairly complex optimization problem, and in fact it's close to or actually untractable because you have a lot of state variables. So when you do counting, it's 3 times 4 times j plus 2, j brands in 4 sizes with associated prices and indicators for feature and display. And these depend on ST, CT, and these choice indicators. And then there's also an epsilon t and nu t involved. So this is too complicated, they figured, to take to the data like this. So they propose a solution, and that solution is kind of interesting. And arguably, it worked in their case. And that is something that is a more general takeaway of that paper here. So let me first describe this very briefly, and then we kind of go back and forth to understand what's actually going on here. So first of all, we have two decisions that are made, and think of this as like a likelihood contribution, right? The probability to observe a particular brand size combination is the probability to observe a particular brand choice conditional on size times the probability to observe a particular choice for the size. So I can always rewrite joint probabilities like that. There's no assumption needed for that. That holds by definition. Furthermore, so why is that interesting? Well, you can think of this as a static problem or a static part of the decision problem, and you can think of that as the dynamic part of the decision problem. Why? Because the size choice will actually have implications for tomorrow, whereas the brand choice does only have implications today. And this is something that I will talk more about also in the following slides. So brand choice conditional on size really only has an impact on today's flow utility. And on top of that, it does not influence the consumption decision today. And that is important. And this is something we will talk about more on the following slides. Okay. So what we will see is that the probability that a particular brand is chosen conditional on size in general depends on prices, advertising activities, inventories, consumption needs, shocks. But actually what we will see is that only prices and advertising activities conditional on size will play a role. So what will not play a role are all the dynamic things in the model, right? It will not depend on the inventory, which is something that has to do with the dynamic part of the model. It also does not depend on the consumption needs, because of course the consumption needs, they do have dynamic implications. So when today I have a high consumption need, then I will deplete the inventory, and that will have negative effects for my continuation value, on my continuation value. But all this does not play a role for my brand choice decision once I do condition on size. Okay, it will have an implication for my size decision, but I'm going to be able to treat that one separately. So what they work towards is a separation between that static brand choice decision and that dynamic size consumption choice. Good. So here this is the formula that showed up before, or the part of the Bellman equation that showed up before. That is the expected continuation value conditional on S, C, and D. And what you can substitute back in is that inventory tomorrow is inventory today minus consumption today plus size choice today. And what they will actually show, what we will see is that this object here, which has a very high dimensional conditioning set, is equal to that object here, which has a low dimensional conditioning set, because what we have here is a scalar. So that is the inventory tomorrow that is known given what I do today. And all this high dimensional stuff is actually translated into this vector omega t. And we're going to look into that in more detail, of course. So omega t is a vector with one element for each size, but it is not related to brands. Okay, and once we are there, what we will see is that for this dynamic choice, the probability that a particular size is chosen today, we also get a simplification, and the simplification is that I don't have to keep track of all these prices and advertising activities, but I do only have to keep track of one number per size, and that is in this vector omega t. Good. So how does that work? What's going on here? One central thing that is going on here is that optimal consumption conditional on X does not depend on the brand. And that is lemma 1 in the paper. So let's think about this a little bit. Conditional on a particular size choice, how does my utility look like? When I purchase brand J of size xt and consume CT, what I'm going to get in terms of utility is that utility of consuming CT, that also depends on my shock, nu t, which is part of my state, minus the inventory cost, plus that brand specific part of the utility, plus my continuation value. So now when I want to think about whether something has dynamic implications, I have to think about that continuation value here, right? And what they then point out is that the continuation value does not depend on the brands that I buy today. Okay, so the continuation value when I buy brand J today is equal to the continuation value when I buy brand K today. Why is that the case? Because in the end of the day, tomorrow when I consume laundry detergent, I will not care about the brand that I've bought in the past. Why do I not care about the brand that I've bought in the past? Well, because the utility from consuming laundry detergent does not depend on the brand. And what that then means is that brand choice, conditional on size choice, is ultimately a static problem. Let's look into brand choice a little bit more. This is the maximization problem that households solve. So maximize utility when choosing the brand. This can always be written, so here we have the epsilon j x t's. This can always be written as the sum of two parts, omega xt and epsilon xt. And this is by definition of the omega xt, because what omega xt is simply the expectation of all this, and epsilon xt is that expression minus the omega xt. So there's no assumption needed for that, but of course this will become very useful once we do make more assumptions. So the maximum here, just to be very clear, respectively is taken over all brands holding the size x fixed, because this is how we think about the decision problem. We think of it as choosing something that has dynamic implications, that would be x, and then conditional on that, or taking that as a given, I'm choosing something else, which is the brand, and that is a static choice problem. And then when we estimate parameters, we first turn to the static part and then turn to the dynamic part. But here the thinking is the other way around. What they assume in assumption 3 is what you probably already expected, namely that epsilon is IID mean zero type 1 extreme value. And what that means is that the inclusive value for size x at time t is the well-known log sum term. Okay, so we have an inclusive value that is specific to x at time t, and that is this log sum term here. So that is the sum over all the brands of the exponential function evaluated at the mean utilities for that given xj combination, and then the log of all that around it. Okay, and what you see on slide 18 is a derivation of that. I'm not going to go through that in much detail. This is really the usual derivation for this. What I would like to point out is the following when I go 2 slides back, and that is exactly the same in a nested logit model, and that is that once these epsilon j x t's are type 1 extreme value, what I will get is that also the epsilon xt is going to be type 1 extreme value. Okay, so we go from brand specific epsilons that are type 1 extreme value to size specific epsilons that are also type 1 extreme value, and that only works for the type 1 extreme value distribution. Now, having said that, what is the dynamic problem? The dynamic problem is to choose x and c, knowing the law of motion for the inventory. So inventory tomorrow is inventory today minus consumption today plus purchased amount today. What I will also know is that the utility contribution from choosing a particular size in t plus 1, xt plus 1, is omega t plus 1 in expectation. And the expectation here is over the taste shocks. This is conditional on prices and conditional on advertising activities. So here we have the omega specific to a particular x in t plus 1 given by the log sum term. Then they make 2 assumptions. Assumption 2 is that prices and advertising activities follow an exogenous first order Markov process. This is not yet enough. The assumption that they really get a lot of mileage out of is assumption number 4. And this assumption is one that you should really let sink in for a moment. So the assumption is, so think of it like this. Today, you're wondering how attractive it will be to buy a particular size tomorrow. Okay, for that you need to form expectations about these prices and advertising activities tomorrow, next to basically taking into account that you don't know your taste shocks of tomorrow. So you're going to form expectations about them too. But this is already embodied in these omegas. Okay, so the taste shocks are already taken care of. So now you need to form expectations about prices and advertising activities. And what they now assume is that the distribution of the omega tomorrow, given all the information today containing the prices and advertising activities, is equal to the distribution of omega tomorrow given omega today. Okay? And when there are 4 different sizes, then I have, for each size, I have a distribution of the omega tomorrow, and it depends on the omega of each size today. Okay, so all 4 sizes today will have an omega today, and all these 4 values will have an impact on the distribution of the omega tomorrow for each size. So under this assumption, and that's a strong assumption, that's an assumption that we can't directly test because it's not tractable to solve the full dynamic model. So at least I'm not aware of any paper that has shown how good this assumption is. It has some, it makes some intuitive sense, but there's no formal result saying how good this assumption is. But given this assumption, it does make sense to proceed in the way they do in the paper. So the first step, they estimate a logit model, multinomial logit model, conditional on size, to obtain the vector of fitted inclusive values, omega t, for each time period in our data. And in the second step, what they do is they estimate the law of motion for omega t. So omega t is a vector containing the omega xt's for all the sizes. And what they assume is normality. So the omega xt, that will be one value, that's a one-dimensional object, is normally distributed with a variance, here standard deviation specific to x, and a mean that is a linear combination of all the 4 omegas today with size-specific coefficients. So with this in hand, we can turn to the dynamic discrete choice problem with the simplified Bellman equation. What you see here is that the flow utility part of the Bellman equation now has the omega in it. So all the brand choice stuff is actually gone. And again, the dynamic problem is that you would choose C and X to maximize your utility. Assumption 1 in the paper is that this shock to the consumption needs, nu t, is independently distributed across time and consumers. And on top of that, there are a couple of functional form assumptions. So the consumption utility function is specified as gamma log ct plus nu t, with log normally distributed nu t's actually, and the inventory cost is specified as a quadratic function in the beginning of period inventory. These assumptions are assumption 1 above about nu t and assumption 3 that epsilon is IID imply that the continuation value has in the conditioning set IT, omega t, ct, and xt. Okay, so IT is one-dimensional, omega t will be four-dimensional, ct is one-dimensional, and xt is also one-dimensional, and ct and xt only play a role because they influence IT plus 1. So IT plus 1 is given by IT minus CT plus XT, as we have seen before. Now, what we need to do next is to actually numerically solve for the values. So let's first think about this in terms of finite dimensions. So what the authors of this paper, Hendel and Nevo, do here is policy iteration. And when you do policy iteration, what you first do is you set up a policy valuation step. So you start with an initial guess of an optimal policy alpha consisting of a consumption policy and a purchase amount policy. These are the two dynamic choices. The consumption policy depends on the inventory, on the omegas, on epsilon and nu. Same is true for the purchase amount policy. For these policies, you can calculate the value function simply by plugging them into the formula we have seen before. So again, this is the flow utility part of the value function, and this here is the continuation value. And what we do now is we acknowledge that inventory at the beginning of the next period depends on consumption and purchased amount today. And for this, we can plug in these policies. And what we will also have is that xt will influence which omega is picked out of the omegas we actually know. And here we have an expectation that uses the transition probabilities implied by policy alpha, which basically means the state transitions for the inventory. This is all based on the initial guess of the optimal policy. And now we go to the policy improvement step. In the policy improvement step, we compute an improved policy CT alpha prime and XT alpha prime. And they still depend on the same variables. So these describe the situation the consumer is in. And what this improved policy maximizes is the value function, but you will only have an effect of that improved policy in the flow utility part of that value function. So observe that the alpha here is not the alpha prime. This alpha here is not the alpha prime. So we only alter things here. We take the continuation value as it is. We take it that this improved policy does not have an impact on the continuation value. And this is, intuitively speaking, to keep things simple. Now, with finite dimensional policies, what we will get when we iterate on this is exactly to the same result as we would get to if we were to do value function iteration. We get to the solution, the exact solution to Bellman's equation. And we get the optimal policy in a finite number of steps. So it's exactly like before. Now, the problem is that things are not finite dimensional, right? And for that reason, we need to do some smoothing. The way this is done is by means of value function approximation. For this, what you do is you say, okay, I'm going to approximate the value function using k basis functions. So think of this as, for a second order polynomial, you have two basis functions, right? So here what we have is lots of interaction terms and quadratic terms and so on and so forth in the state variables. Once we impose this, what we can do is we can solve for the coefficients on these basis functions by minimizing a distance or by solving a system of linear equations. And this is useful to compute the improved policy. How exactly is that useful? Well, the improved policy is obtained by keeping the continuation value what it is and finding a better policy that gives us a higher value of the sum of flow utility and discounted continuation value. For this, what you will need is still the derivative of the continuation value with respect to the choice variables. And once you have such a formulation or such an approximation of the value function, it's relatively easy to get these derivatives. Just think back of a polynomial and taking the derivative of a polynomial. It's very easy to obtain that as a function involving the basis functions or transformations thereof and these theta k's. Now, all this gives us an approximation to the choice-specific value function. It's now written here as a little v. The first arguments describe the state the household is in, it, omega t, epsilon t, and nu t. And what the household chooses is ct and xt. Here you have the flow utility part of that value function. Here you have the continuation value. And in terms of what do we have data on, xt is observed, omega t can be treated as known because it can be estimated. As we saw before, this was the multinomial logit exercise we did. The next thing to think about is the inventory. First of all, notice that we now have a consumption policy or an approximation to the consumption policy. And what we can do with that is we can always generate the distribution of the inventory of period t plus 1 given the inventory in period t. Why is this a distribution? It is a distribution because it depends on nu t, and nu t is a random variable. Now, what it also means is that once we assume an initial distribution for the inventory in the first period, that we can derive the likelihood of observing the sequence of inventories that have then later generated choices that we see in the data. Next, let's think about the epsilons. So epsilon xt is an additive error term. And that means that actually the choice-specific value function has it enter additively, and we can write things like that as a v bar plus epsilon xt. And on top of that, we have that the probability that the household chooses a particular value of xt, that is the quantity choice given the inventory that we can reconstruct, as I just told you on the previous slide, as this integral here. So what we do here is we use these v bars. This is just really the multinomial logit formula because I have 4 choices for x, and each of them has like a mean utility and a type 1 extreme value choice, taste shock. So I'm getting this multinomial logit probability here, conditional on nu t, and then I'm integrating out the nu t just as I would do it if it were a random coefficient. This brings us to the results. So if you want to have a little pause, now is a good moment to lean back, get a cup of coffee, and then come back after that. What we see here is a table with different specifications for the first step. So this would be brand choice conditional on size. So again, what they did here was relatively straightforward. Suppose you see a household buying a particular size, then you reconstruct the choice set, including all the brands for that particular size. So you need to assemble all the characteristics, basically. And then you estimate a multinomial logit model, and later you're going to use that to reconstruct these omegas that are size specific. And what you see is here various specifications, and what you do see, for instance, is that feature and display have a positive effect on brand choice. The price coefficient does vary across specifications, and yeah, so it is not completely robust, but that's also not the focus of the paper. Second step would be to estimate the price process, as they call it here. So this was this part of the model where the omega in the next period is a linear combination of the omegas of the previous period in the mean, and you impose a normal distribution. So you also estimate the variance of that process. So what you see is that the omega 2 is best predicted by the omega 2 in the previous period, and the other ones play relatively little role for that prediction. The omega 4 actually does play a little bit of a role. Omega 4 is best predicted by omega 4 in the previous period. Here they also include additional lags, if you like. And then they also have like a different process for each type, but let's not focus on that now. Finally, here are estimates of the dynamic parameters, and these are relatively few to keep it doable, let's say. Inventory costs, quadratic, so you get concave inventory costs. The quadratic term is negative, at least. So what they do here is they estimate this for different types of households: urban markets, suburban markets. So they have 6 types of households, and then they divide up by household size. For almost all of them, it's concave. Here the quadratic term is not significantly different from 0, but otherwise it looks pretty reasonable. This is the gamma parameter of the consumption utility, and that's already it. So in order to assess whether this makes some sense, what they do is the following exercise. They say, suppose the beginning of period inventory is 30 ounces. Then buying a 128 ounce bottle instead of a 64 ounce bottle increases the storage cost by, depending on which household you look at, 20 cents to 75 cents. The savings associated with doing that is roughly 40 cents. So some types of households would buy a larger bottle and some wouldn't. Another thing they do is they look at the hazard rate of purchases. So that would be the likelihood of purchasing so and so many weeks after the last time, given that you haven't purchased yet. And here you see the data. So this would be with the diamonds and the dashed and the dotted line. So you see some wiggles here that will be hard to generate with this model. And here, this is the simulation coming from the model with the estimated parameters. Okay, so you don't see like a perfect fit, but arguably the patterns in the data are matched pretty well. What you see here is long-run own and cross-price elasticities. So for instance, this number here, minus 2.916, is the percentage change in the demand for whisk 128 if the price of whisk increases by 1%. And that is a fairly typical number that you get here. So something between minus 2 and 5, 6, 7 is to be expected. And they do find these numbers here. The motivation of the paper included the claim that you might make a mistake when you estimate these elasticities using a static model. So what they have done in table 8 is to show average ratios of elasticities computed from a static model to long-run elasticities. And what that shows is that you would overestimate own price elasticities and you would underestimate cross-price elasticities. And what's happening here is quite interesting. So part of the intuition is that when you estimate a static model, then what you do is you take variations in prices and you correlate them essentially with a variation in demand. Okay, but what that does is it does put a lot of weight on short run variation. So when you see in the data that prices go down and subsequently a lot of people buy, then you will conclude that the price response is big. But part of that price response is just stocking up. So when actually prices would go down permanently, then the price response would be smaller. Okay, and this is exactly what a dynamic model would tell you, but the static model would tell you that price responses are actually bigger. So that is the reason for you overestimating own price elasticities. Good, so this is what I had for Hendel and Nevo to give you at least a glimpse into this fairly complicated paper with lots of bells and whistles. What I do really like about this paper is that one can get ideas about making simplifying assumptions, especially one can get ideas on how to break up a very, very complex decision problem into a static part and a dynamic part. And that might be useful for you in some of your own work. In any case, I think what's nice about this paper is also that it makes it all work and it demonstrates that we get different elasticities out of such a model than we would with a static model. With this, all the best.